So the first thing to say is number 9, I did my answer key wrong, so I fixed it on the back end. So if you count all the red marks where I had wrong answers, add them up, the number at the top should be that number minus 1. So if you got that, and then huh? No, I've already done it. I mean, I've already calculated your grade. It's in D2L. You see your grade in there, right? So it should be, how many? 36 minus however many you got wrong, divided by 36 times 100. It should be what's on D2L. So double check that.
Could you go ahead and go on the slide?
Yeah, I'll go with this. Let's go with the test first. I was going to do some redox reactions too, but maybe we'll do the lab after that first. And then stop. Any specific questions on that? Maybe I'll just go through it. You want me to just go through it? Question 1, significant figures. If there was a decimal there, there would be 4 significant figures, but without the decimal, it's just 2, so that answer is 2. The second one, if you multiply that, the first number, that's 3 significant figures, that's 4, so your answer should have 3. And is that one B or C? That was a 2B. 0.126. If you round it correctly. Did you calculate it? Did you calculate it? Calculate that real quick. This times this. Sorry, what is it? The 3 significant figures, the 3 does not round to 6. So what do you get when you calculate this? 3.5 minus 1.21? 2.25? 9? Yeah. Sorry? 2.39?
Oh, no, I'm sorry, I was just saying it rounds to significant figures.
Yeah. All right. So when it's addition subtraction, you just look at what's after the decimal. This has 1 after the decimal, this has 2. So your answer needs to only have 1. So we're keeping those. The 9 rounds to 2, so 2. Standard scientific notation. So for standard scientific notation, we want the decimal to be right here. I always pick up the bad marker first. So 1, 2, 3, so we want 6.84 times 10 to the 1, 2, 3 times 10 to the negative. And that is B. 5. Meters. Convert that to millimeters. Formally, I would go millimeters, meters, 1,000 millimeters. That is your conversion factor. If you multiply this by 1,000, 1, 2, 3. millimeters. So that was B. Okay. So 181 grams. What is the volume? And you're given density. Density is 2.20 grams per milliliter. Or the way I tell you to write that is 2.20 grams to 1 milliliter. So you're going to use that, but you need the grams to cancel and to end in milliliters. So I can't use it the way it is, I need to flip it over. So I want milliliters on top and 2.20 grams on the bottom. Now grams will cancel and will be in milliliters. So 181 divided by 2.20 is E, 82.3. Three significant figures, three significant figures. That's exact, that's exact. Three significant figures. Another density problem. Liquid has a density of that. You have 420 milliliters of it. No, 4.20 milliliters. I just put that over 1. You can use this as is, because milliliters need to be on the bottom. And now it's multiplication. So 4.220 times 1.15. 7. I have E. Is E. 7 E. Ounces to grams. So you have ounces. You need ounces to grams to convert it. So I'll put it here. I put 1 ounce is 28.35 grams. That's exact, and that's exact. So 4 significant figures, 4. So this needs to be 4. 8, my answer key shows D. 6 feet right. The next one, the pole is on the help pages. Do you know how many centimeters there are to an inch? 2.54. But which is which? Inches or centimeters? What I had here was the other way around. This is somebody's page. Instead of 2.54. Something else. Anybody still have their help pages on there? The back, well, I would have had back there in the help pages. There was. Yeah. Do you have that? That's essentially 1 divided by 2.54. 3937, is that what it is?
Yes.
Either one of these should give you the same answer. This number is just 1 divided by 2.54. Either way, you should get the same answer, which was number 9. B. You should get 1.78 either way. It still should come out with 2.98. 1.17. Well, this came out with 1.17. 2.98 times 0.3937. Yeah, 1.17 inches is what you should get for that. I've been terrible with math this semester. Do every equation wrong once. Where are we? Predict the charge on selenium. So, everybody say that. Selenium is below oxygen. It's just like oxygen. So what's the charge on oxygen? So that'll be the same for selenium. So that one should be -2. D. Number of electrons and protons in the calcium atom. So if you look on the periodic table, if you find calcium and you see 20 for the atomic number, what does that mean? That's the number of protons. That's the number of protons in calcium. The number of protons in calcium 2+, though, the ion, it has lost 2 electrons. So the electrons are -2 of these. So the electrons are 18. Some people missed those. Does that make sense? For the neutral atom of calcium, it's 20 and 20. But once you get the ion, you still have 20 protons, but you only have 18 neutrons. Make sense? How many protons in phosphorus? You just look it up on the periodic table. It says 15, so that should be A. How many electrons are in each neutral atom of iron? If it's neutral, it has the same number of electrons as protons. So again, you look on the periodic table, you find Fe, you see 26, so that one should be D. How many neutrons does Cl35 have? Well, first, find out how many. So this is the mass number. You need to know how many protons chlorine has. Chlorine has 17 protons, and then you subtract. So 35 minus 17 is what? 18. That's right. So that one should be B. Okay, ionic compound. BeS. What's the charge on Be? Well, if you have your periodic table, you see it's there. So that's going to be 2+, and sulfur is what? 2-. So the formula is just BeS. And it's D. 15. Yes, checking my answer key as we go. Magnesium fluoride. What's the charge on chlorine? Fluoride. -1. And for magnesium, that one's 2+, so you have to have Mg2 to make the charges balance. That was B. All right, the name. What's the name for Cu? I didn't tell you that Cu was copper, but it should have been obvious, because copper is in all the answers. But what's the key here to naming it? Copper is one of the transition metals, so you don't necessarily know its charge. You have to find its charge, and its charge has to be in the name in the parentheses. What's the charge on phosphorus? They didn't bring a bunch of periodic tables today. Charge on phosphorus. It's right below nitrogen. There's periodic tables back there. You can see it. Phosphorus is just below nitrogen. So what's the charge on phosphorus? So phosphorus -3. We have 2 of them. So we have a total of -6 charge. This isn't charged up here, so I'm going to say equals 0. So what needs to be here to make this true? All right, and we have 3 coppers. So we have to split that +6 among those 3. So what is each copper going to be? 2 plus. So the answer is copper 2. So it should be B, right? Okay, titanium cyanide, titanium 2 cyanide. Maybe it's obvious from the answer there. Cyanide is this polyatomic ion, and it's 1 negative, and I did give you the page with all of them on there, so you should have been able to see that cyanide is Cn, and it's 1 negative. All right, in titanium 2, because of that 2 there, we know it's 2 plus. You with me? So we're able to tell because this was named titanium 2. So that means we need 2 of these for every one of these. So it's Ti Cn2. If you did Ti Cn2, that looks like there's 1 titanium, 1 carbon, and 2 nitrogens. But what we really have is 1 titanium, 2 Cns, and another 2 Cns. So there's actually 2 carbons here. So that's why this is wrong. So that one should be Ti2 is, the right one would be C. All right, what is the charge on iron fluoride? FeF3. What's the charge on chlorine? -1, and there's 3 of them. So we have a total of -3 charge. There's no charge up here, so 0. What needs to be here for this to be true? +3, and there's only 1 iron, so it gets that whole charge, +3, or 3 plus. So that one should be B. What mass in grams? 2.48 moles of nitrogen weigh. You look on the periodic table, and you find out that nitrogen is grams per mole. That's what you get off the periodic table, which is 14.01 grams of nitrogen to 1 mole of nitrogen. We want moles on the bottom, so we can use this the way it is. 14.01 grams of nitrogen to 1 mole of nitrogen. Moles of nitrogen cancel. We get grams of nitrogen, so we just multiply 3 significant figures, 4 significant figures, so answer should be 3. And what do we get? Number 20. E. 34.7, is that what y'all got? guess that's right. Was it 34.7? So the answer would be, how many moles are 8.16 grams? 21, how many moles are in grams of rubidium? I kind of told you where to find it on the periodic chart. Rubidium is all right, so it wants to know how many moles. So I'm not going to use it like this. I'm going to use it flipped over so that the grams cancel. So I put 85.47 grams of RB. 1. So you're ultimately dividing 3 significant figures, 4 significant figures. Your answer will be 3. And I guess if you calculate it out, you get B. This is 0.00955. Moles. Right? B. Is it B? B. How many moles of aluminum? 488.26 moles. So it's that many atoms of aluminum. No unit. So we need no unit. There's the unit. So ultimately, I would do this in my calculator. 22 is A. So I get that for the answer to this, and then if I move the 10 to the 23 up here, and make it negative, 26 minus 23 equals 10 to the 3. So yeah, A, that should be the answer to A. Okay. 23, did you get 23? Everybody got 23? How many grams of this are generated when you use this many grams of this? That tells you you're going to need the grams per mole for both of those. 12.6 grams of AgNO3. We're going to need grams per mole for AgNO3. And I gave it to you so you didn't have to calculate it. AgNO3 is 169.87 grams to 1 mole. So grams of AgNO3, grams of AgNO3, those cancel. Moles of AgNO3 has to cancel next. And this is where we go moles to BaNO3. And that you get from the equation. So there's 1 mole of BaNO3 to 2 moles of AgNO3. Those are the coefficients from the equation up above there. So now moles of AgNO3 cancel. Now we need moles of BaNO3 to cancel. BaNO3 2. And that'll get us to grams of BaNO3. And the grams per mole for that I gave you as well, 26.1. And that should calculate out to 3E 9.69. That's exact, that's exact, that's exact, that's exact, that's exact. 3 significant figures, 5. 5 significant figures. Yeah, so that's why we're down to 3. So 5 significant figures, 5 significant figures, 3 significant figures. So we end up at 3 at the very end. How many moles of O2 are needed to produce moles of CO2? Grams are not mentioned, so you're not going to need that term and that term. You're only going to need this for that equation. So it says 5.94 moles of O2, and moles of CO2. Since you only need that one relationship, moles of CO2 goes on the bottom. Moles of O2 on top. And that's all you need. And the molar relationship is there's 7 O2 and 4 CO2. So you calculate that out, you get an answer. Moles of CO2 cancel, you end up in moles of O2. 24 is A, 10.4. Moles of O2. Right? It's A. Okay, got A on the answer keys. Assuming you all agree. This one I probably just should have said electron pairs. Did I tell you to cross out non-bonded? So you have this molecule. Okay, the key here is this. We've got hydrogen, we've got carbon, we've got oxygen, and we've got nitrogen. How many valence electrons does hydrogen have? It's 1, so I'll do that. How many valence electrons does carbon have? 4, so I'll go 1, 2, 3, 4. Oxygen has how many?
6.
So I'll go 1, 2, 3, 4, 5, 6. And nitrogen? It's 5. 1, 2, 3, 4, 5. Okay, you can look at that and you get this information from it. The single electrons, the ones that aren't paired, that tells you how many bonds it'll make. Put this over here. So hydrogen will make one bond and it has no lone pairs. Carbon will make 4 bonds, it has no lone pairs. Oxygen will make 2 bonds and it has 2 lone pairs. Nitrogen will make 3 bonds and it has 1 lone pair. So you can ignore the carbon and hydrogen, there's no lone pairs on those. But there's 2 lone pairs on every oxygen, and there's 1 lone pair on any nitrogen you see. So we have 1, 2, 3, 4, 5, 6, 7, 8. Well, actually, I should go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm doing it wrong again. I'll just draw them all in. So there's 2 there, 2 there, 2 there, 1 there, 2 there, 2 there. 2, 4, 6, 8, 10, and 1 more makes 11. So there's 11 of them. So the answer there should be A. How many covalent bonds are generally formed by atoms with 6 valence electrons? Well, that was oxygen, or anything below it. Any of the nonmetals below it. So how many bonds will this make? It will make 2. 1, 2. All right, you've got carbon. No, you've got carbon, 3, hydrogen, 8, and an oxygen. So how many valence electrons for carbon? There's 4, and there's 3 carbons there, so there's that. How many for hydrogen? 1 for each hydrogen, and there's 8 of them, so there's that. How many for oxygen? There's 12 plus 8 plus 6. Is that 26? So the answer should be B. Right. And I've got carbon up here for the next problem. Correct Lewis dot structure, and that is D. Correct Lewis structure for sulfur. Sulfur is just below oxygen. So really I can do this. There's sulfur. It doesn't matter where the pairs and the singles are. I hope it didn't trick anybody, but I did say in class that that's perfectly valid. As long as you got 2 pairs and 2 singles, it's legitimate. So E should be the answer there. Okay, solubility. I gave you the solubility chart. But on the chart, if you looked at Br, it says anything Br is soluble except, and lead was one of the exceptions. So that one should be insoluble. So that should be B. Soluble, insoluble, soluble. Okay. This one, if you looked next to S, I don't have the chart with me. It's 30 and 31. Okay. But if you look at sulfur, one of its exceptions to not being soluble is sodium. So this one is soluble. Right. Yeah, AgNO3. All nitrates are soluble, so that one's soluble. There's no exceptions for nitrate. Calcium phosphate. C2. Okay, 33. So all phosphates are insoluble with some exceptions, but calcium was not in the exceptions. So that one's insoluble. 34 is insoluble too. You look at SO4, and it says all of these are soluble except for these, and barium was an exception, so that one should be used. That just came down to being able to use that chart. I gave you the chart. Okay, so we're down to net ionic equation, total ionic equation. So all sulfates are soluble except for a few things, but this is not one of them. Oh, I just gave you that part. Aqueous, and I told you this is the solid. All right, the total ionic equation is Cu 2 plus aqueous plus SO4 2 plus aqueous plus 2 Na aqueous plus 2OH aqueous 2Na aqueous SO4 2 minus aqueous plus CuOH, and you leave that solid. That's the total ionic equation. Did you get that one? And this one was the net ionic equation.
He switched it around. The one he just did was, the total, and then maybe the hours.
Oh, did I? So I'm glad I didn't erase it. So the net ionic equation here is you keep the CuOH solid, and you only keep the ions that went into this. So I'm keeping this, I'm keeping this. So that's the net ionic equation. And you also could have done this by looking up here, and everything is the same on both sides. You cross out. I guess I didn't ask about spectator ions, but the things I just crossed out are called the spectator ions. So if you cross those out and you bring down what's left, then you end up with that. All right, so total ionic equation. 2NaI. I can give you this one. Aqueous 2NaI. This is aqueous. All nitrates are soluble, so you would have had to use the solubility chart to see those. And then PBI 2. This is the solid. So now the total out equation is PB2 plus aqueous plus 2NO3 aqueous plus 2Na plus aqueous plus 2I aqueous. And leave the solid as is. And that's what should have been the answer. B. Is it B? All right. So that's the test. So everybody got the test and their answer B. What should we do next? Was everybody able to make a graph? Anybody not able to make a graph? I know one person already said it. Did you leave? Who needed to make a graph?
I just need help with number 2. I have the graph.
Anybody have their lab book with them? I didn't bring them. Your lab notebook, your lab manual. Somebody's got it. Graph of that line of absorbance to concentration is this. Absorbance equals, that's called the molar absorptivity. V is the distance through that cuvette, and C is concentration. All right. The distance through the cuvette was 1 centimeter. And so if you did concentration, that's the C up there, and it would have been in molarities. And up here you had if you did a graph correctly, you should have gotten something like this. For the line of best fit, your data might do this. Did anybody have trouble getting a generally linear plot by messing with some data points? I only saw one lab that I had to mess with a little. But, and it gives you, all right, there's no plus B here, but you know what the B is? What do you call that? When you do y equals mx plus b, what is b? What is m? That's the slope. And what do you remember what b is? It's the y-intercept. It's where this hits this axis. Technically, it should be 0, just because of the way this works. I mean, if there's none of the analyte in there to absorb, then it should absorb 0 when there's 0 concentration. Anybody have their equation off their graph handy? Do you have yours?
Yeah.
What did Excel tell you for this formula?
Like for the Y?
Yeah, well, the whole thing.
I got Y equals 4 point. Oh wait, for the gear one? Gears one?
Well, I mean, you made a graph, and then you made a line of best fit, and then you asked Excel to give you the equation of that line.
Yeah, so that I got Y equals 4.1834x plus 0.044. And then R squared is 0.99.
0.99 something, okay. Good. So the 99 tells you it's a good fit for your data. See how close to zero that came? I mean, it was within a 100th. But this is just experimental error that this is not zero. But X was the concentration. So that's X. You can ignore B for this. So what that tells you is that equals for yours what were our significant figures here? Absorption was 2 or 3 significant figures. What did you get significant figures for the concentration? I think that would have been 2. What I'm getting at is we'll probably just need to keep 2 of these. 4.2. And the B is 1 centimeter. Molar absorptivity. Yeah. Our molarity centimeter. Right. Yeah. It might say the units are m to the -1, c m to the -1, but that's what it means. They're both underneath in the denominator. But so the B, the 1.0 centimeters, makes the centimeters cancel. And since it's just a 1 numerically, you can just get rid of that and go, this in molarity equals 4.2. Centimeters cancel. Yeah, that's right. No, I shouldn't do that. Let me do the algebra. That's concentration. Let me do the units like this. In molarity. And E is 1 over molarity centimeter. And B is 1.0. B equals 1.0 centimeters. Right, okay. So divide both sides by this, and you get the molar absorptivity units of 1 over molar centimeter equals 4.2 molar per centimeter. Something's wrong. I tried to do the algebra right. Per centimeter. Why do I have that? We did concentration, not 1 over concentration. Anyway, I don't know what I'm doing weird with the units, but what you're finding is 4.2 for your molar absorptivity in your case. Molar absorptivity is literally just this to 2 significant figures. Yeah.
Thank you.
Why is the units going wrong? Yeah, go with that, that's fine. It's because absorbance is unitless. So the units should cancel out. That was number 2. So that's how, is that what it asked for? Use the slope of the line to determine the molar absorptivity. So that epsilon symbol is the molar absorptivity. If you read a few pages in this lab, I think you can find all this information. We don't go over Beer's law in class. At least I don't. It's a spectroscopy thing. Okay, anybody need help making their graph though? I can take the data and help you. Okay. Any other questions on the lab? You know what we were supposed to do? And we didn't have any. This line is like a calibration curve for the concentration of, what was it? Blue number 1 dye. And I looked for this and I couldn't find it. And apparently trauma had put it away and I didn't know where it was. But this is Gatorade, this color is a blue dye number 1. What we could have done is taken some of this, found its absorbance right at the beginning of the lab, and then we set that fact, let's say it was right here, and then we set that fact aside, and then we got what we knew the concentration of the blue dye, several different concentrations. And we get this, and essentially we would be able to say at the end of lab, that's the concentration of blue dye in the Gatorade. Or actually, this is the qualitative way to do it. The analytical way to do it would be to plug in whatever we got for absorption for Y, and then solve for X, and that gives a more analytical description of where X was. But labs still work, we just didn't get the sort of punchline at the end. Okay. No more questions about lab? I wanted to go over a little more, just reiterating redox reactions. And I found a bunch of good ones. I am going to go about getting this stuff in D2L so you have stuff to practice this week. And hopefully we can look at it before you go on break. So when you come back to break, it's not all like, because you're going to forget everything over break. And so on. So I always did anyway. So let me try some, I found some good redox reactions online. The book didn't have much there. So let's say we have this reaction. I had the rules written over there the other day. But this mostly comes down to keying in on oxygen. The rules there were like, if you have elemental like this, I should probably have solid there, and this would be a gas. I'm sure this was a solid. Being listed. Elemental means it's all made up of just one atom. In that case, the oxidation state is 0. And then when it comes to these, the oxidation state is the charge that you would typically put on them. The only weird ones are the polyatomic ions, where I would be like, I would go, okay, oxygen 2 minus, 2 minus, 2 minus, 2 minus, there's 4 of them. So minus 8, the charge is minus 2. So what needs to be here to make this true? Here we go, plus 6, and that means S is 6 plus 6, which is not its typical, that's not sulfur's typical charge state. So it's really these weird polyatomic ions that you do this for. The rest of it should be just like when we were doing ionic compounds. Okay, do you see anything elemental up here for this one? Where only one atom is involved. Or one type of atom. Yep. This one's oxidation. Oxygen is 0 here. And we have aluminum by itself. The S just means it's solid. The 4 is just the coefficient to make everything balance. So that one's 0 as well. If we go over here, this should seem familiar. Oxygen, -2, -2, -2. Total of -6 charge. No charge here, so I'll say 0. Aluminum has that predictable charge though, so you can kind of see where we're going. This should be a +6. There's 2 aluminums. You got to split that +6 among the aluminums. But you probably already knew that was the charge on aluminum, right? Minus. So, now I want to say, here's aluminum at 0, and here's aluminum at 3+. Here's oxygen at 0, and here's oxygen at 2-. Which one had its charge reduce? Through the reaction. Starting here, going over there, which one had its charge reduce? Huh? Aluminum went from 0 up to +3. Oxygen went from 0 down to -2. Oxygen, I tell you this to come up with which one's charge reduced first, just so you can go, that's reduced. AKA it underwent reduction. And one more thing I can say here is it gained electrons. I'm going to do E-. 3 things I can say about oxygen here. They're all kind of synonyms. It's reduced, it underwent reductions, and that means it gained electrons. That means its charge went down. And that necessarily means this other thing was Aluminum was oxidized, it underwent oxidation, it lost electrons. You okay with that? Definitely going to have questions like this on the test. Which one is the reductant? Reductant. There's, you could say the reducer and I know it's crazy, but all these words are used. Aluminum is the reductant because it can cause reduction. It's the reducer because it reduced something, the oxygen. It is the reducing agent. And then it flip-flops when we go to oxygen. This is the oxidant. It is the oxidizer. It is the agent. These that I have circled are all referring what it does to something else. A reductant causes reduction. A reducer causes reduction. A reducing agent causes reduction. It's causing reduction over here. You okay with that? I know it's a little screwy, but this is not SO4 2 negative. This is actually neutral. SO2 is actually neutral. Look for the charges if you're worried, because it might look like a polyatomic ion. But we're still going to go through the same process here. Oxygen, there's 2 of them, -2.